All right, welcome back. We will now have two shorter talks. The first talk is given by Jeff Agar, and it is about mass spectrometry. Jeff has been at our workshop for the past couple of times and taught sections and given presentations, and we look forward to hearing your latest presentation. Thanks, Jeff.
Thank you, Karsten. All right. Okay, so here's our summary. This talk is in two parts. The first part is practical stuff to help you do protein mass spec and to teach you some new things that we can do with metalloproteins. And that part will be boring. Part two, I have some recent developments in high-res mass spec and their implications to spectroscopy. And that part will be complete hogwash. So get ready, buckle up. Okay, so it is really important. At this same conference in 1998, I was teaching MCD, Raman, and EPR sections. And I love spectroscopy, but I love to study diseases as well. And so the choice to study a human disease where I was purifying proteins out of people's spinal cord and brains with 1 milligram of tissue left me fewer choices of analytical techniques. And I just went there never knowing what would happen into this mass spec community and then never came back for now until this talk. Okay, so the first thing is, PTMs. It's really a great discovery method, and we know where our light is shining and where at least is being absorbed, but the mass spec can help you see other places. Not too many other techniques can boast attomole sensitivity, and that's very conservative. We're very often detecting in the zeptomolar range. If you go far enough down in the zeptomolar range, right, you run out of molecules. That's the end of it all, right? That's it. Okay, quality control of protein expression. I can't overemphasize this. I ran a facility for a number of years. I've probably analyzed 300 or 400 different proteins from different groups. And can you imagine that probably 95% of the proteins that people bring me are not what they think they are? Different N-terminus, different pieces, different sequence, disease-causing variants. I've seen it all. And I did this in one of the labs. I just told this, it looks like 100 people here, and I just said 95% of the proteins are wrong. And in your human brain, you inverted that and said, okay, it's not mine. Right? But I want you to embrace the statistics. It really could be you. Okay? It's unbelievable. I know. It's funny how our minds work. Okay. So the mass spec illuminates distant areas of the protein. This is really important. I have a slide on that next, so I won't go into it. It's great. You can do reaction mechanisms. Mass spectrometers measure mass to charge. You change the charge, you change the mass spectrum. This is really neat. In the last few years, molecular mechanics, molecular modeling have become good enough that with a few constraints provided from mass spectrometry data, for example, some cross-linking one residue to another between a complex of two proteins, you could solve de novo structures, okay? Or for, let's say, for example, intra-subunit cross-linking. This is enough to solve a three-dimensional structure that are really reliable. This is something powerful, and it's very, very new. Mass spec is fast. You can have your results in a few seconds. And everybody knows sophisticated instrumentation is fun. That's just so true. And this field will really keep, and I've seen a lot here, really impressed with some of the instrumentation you guys are developing. I love it. Okay? So, on to the part of, looking at the rest of the protein. Don't be this guy. We all know this story, right? Here's the guy, the cop comes up, what are you doing under the light? And he says, well, I'm looking for my keys. Well, why are you looking under the light? He says, well, that's the only place that I can see anything. It has nothing to do with where he lost his keys. Now, if you don't appreciate this analogy, that's your protein, and the metal is circled. And that is your light source. So now hopefully that's full. And I mean, could this be circularly polarized? I mean, I can say. Kitty, LCD people. Okay. I could do that because that used to be one. Okay. So apropos to this, part of why mass, and I'm going to get this actually, this theme will go through the talk, but part of why mass spectrometers are so advanced really airs back into they were, the charge to mass ratio, or it was charge to mass back then, of the electron was discovered on a mass spectrometer. Thomson won a Nobel Prize, trained Aston, he won a Nobel Prize, trained Rutherford, another Thomson, and 7 or 8 Nobel Prizes came out of those out of the Cavendish lab. It's really a great story to read. Wonderful. And what impresses us to this day is the mass spectrometers that they made in 1920 were actually respectable, have similar performance characteristics to a MALDI-TOF of today, albeit not quite the mass range. Anyway, around 1940, unfortunately, Lawrence invents the cyclotron. That's great. That's a quarter. Wins a Nobel Prize for that. Somebody realizes you can use mass spectrometers to purify uranium. We know this inauspicious. This is a person. Look how that's a relative size. Now watch what happens. They build one. That's one mass spectrometer. Another. They build these into tracks. They put the tracks into buildings. And a lot of development money went in here. Not a great result. This is Lawrence wondering where all of his quarters went, because there's magnets everywhere. And notice proof that mass spectrometry has been, really gender neutral for a long time. Everyone operating there is a female. 1940 something. Okay. All right. Another thing, just for fun, we gotta have a little fun in the boring part of the talk, is that every single spaceship and most astronauts have a mass spectrometer or two. And so on this one, that's an example of the mass spectrometer that was, I think this was Saturn. And there's some really funny stories. Ask me offline about how it broke, and then the mass spectrometrist fixed it while he was on a flight, convinced the pilot that it was to call NASA. True story. Okay, so all this money that's been being poured in for nearly a century. So take a look at this. These are transistor counts. People love to show their Moore's Law plots. I want to puke every time I see them, so I'm going to show you one too. This is on the log scale, so right, linear log. This is an exponential increase in computation speed over a long time. And actually, it's funny. I've seen this plotted back to the abacus, and actually, it doesn't work to the abacus, but it works to print cards and really rudimentary devices that were there in the 1700s. And if you look at genomics, we can't ignore that. Look what they've done. There's your Moore's Law, and then they've had hyper-exponential growth. Really, really something. I made this one for mass spec. This is the number of proteins we can identify per mass spec experiment. Started in '83, moving up to 2013. And while it's not hyper-exponential, it's respectable. Okay? And in this experiment where we're identifying 10,000 proteins, also seeing 10,000 phosphorylation sites, 20,000 glycosylation sites. And if you're wondering what the data all means, I am too. But they have the data, okay? So, and a lot of false positives. It's really nasty. It just really needs some statisticians. Okay, anyhow, so now let's get into what we can do with intact proteins. Most of what you're used to with mass spec and most of what people do is digest the protein. It's the first thing they do. And then they do liquid chromatography mass spec. Now, in that step, of course, the metal is lost. I think that goes without saying. Or if it isn't lost, you have 4 peptides with histidine sort of just flopping around, still bound to your copper. There's not much left of it, okay? It's not the same. So you want to keep the protein intact. And I'm not going to get too deep into the methods here because I want to get on to the hogwash part of the talk. But this is a neat one where, if you look at ferric cytochrome C, or B, this is the experimental data, theoretical data for whether it's ferrous or ferric, okay? Now, it doesn't show up well here, so what I did was, okay, here's their experimental data. This is intact protein. This is one charge state. That's the fit, the best fit to the data, and that is ferric. And this would have been ferrous, or well, it had it, okay? And so you can really, I mean, that's right, quite a nice thing. Now, what you'll have to understand, though, is that the electrospray source is an electrochemical cell, and it's actually very oxidizing, so do be careful. John Amster's done stuff with this, like this with iron sulfur clusters. You could do it, but you have to be careful to just be aware of artifacts that you might oxidize things in the source, and so you might have to do some tricks to keep it in nitrogen. Good news, there's nitrogen coming out of the mass spectrometer and going in, so if you wrap it up, it gets better. Okay? And in this one, you can do this with other proteins. This is myoglobin. Okay? Now, and this is just the thing about no matter what we did, we couldn't stop it from being oxidized. Or we couldn't stop. We would reduce things with dithionite, and yet it would get oxidized. Now, these guys that work at the National Magnetic Field Lab, they haven't taken the anaerobic purification course here, or they'd be fine. Okay? All right. So just do this. If you don't read the supplementary stuff, or if you need to do it, you're not going to get signal usually out of a protein in a mass spectrometer. And so read that. You usually break your protein, and you usually lose the metals. You probably break the liquid chromatography setup. That's really true. Intact proteins have a tendency to do this. And if you get a signal, the data is going to be misinterpreted with metalloproteins. So those of you who've taken the mass spec lab, you know what I'm talking about. The really quick part of the story is that mass spectrometrists are trained by an algorithm, and the algorithm is that they're going to take the mass-to-charge ratio that they observe and multiply that by the charge to get a mass. Now, that'll be the mass of your molecule in the mass spectrometer, okay? But you put on some extra protons, and they assume every single time that those charges came from protons. They subtract them away, but if they're holes, then your mass is wrong, okay? So in a nutshell, that's what it is, but there's... Okay? It's interesting because so many things have been chopped up, metallocofactors are missed during mass spec. And that's just the way it is. Okay. This is all there online. The point here is with protein sample prep, just keep in mind purity is, there are 2 or 3 definitions. So there's purity of your protein, so there aren't other proteins. I would rather analyze an impure sample with, I sound like a priest saying that, but an impure sample with no salt, and especially no detergent. I lost 6 months of my life to Triton contamination. I went to work in a hospital after my PhD, and I would purify proteins, and I would always get a signal by MALDI because MALDI doesn't mind detergents. In fact, it can help them. That's on one of these slides. But I couldn't get electrospray signal for 6 months, and finally I figured out it was Triton, and then I kind of had to quarantine an area of the lab because just in a molecular biology lab, they're swimming in that stuff. All right. Now, we said that already. Keep in mind a couple of little tricks. If you have detergents, this is one of my favorite things. Somebody has, molar SDS, and they try to put the molar SDS through a 3 kilodalton filter. And I understand that the monomer weight of SDS would lead you to believe that's possible. There's this thing called critical micellar concentration, and above which that's just a ginormous ball of SDS that's never leaving your centricon. So I've seen people try 10 or 11 cycles. It's just great. And you don't tell them. It's a rite of passage. All right. Now, reverse phase LC doesn't remove a lot of detergents either. Okay? All right. So I said that this is it. So I've made this nice little, or not nice, it's beauty's in the eye of the beholder, I suppose, but this is a little flow chart or decision tree that you can use, and this points to different workflows in the back of this lecture, okay? You can read them, it gives you all the seminal literature, and then you can do what you need to do. Now, for you, most of the time, the thing I want to point out is if you have detergents, and you want an intact protein molecular weight, invariably that leads you to MALDI, although there's some tricks around that. And MALDI, you're not going to maintain your metals. Interestingly, if you do MALDI of small molecules, they do often maintain their metals. So if you're a cofactor person and you're synthesizing it, you're probably okay. But anyway, head this way for everything else. Okay. basics of the mass spectrometer, just to let you know that the operational principles are simple. There are only, these days, there aren't only, but these are the three major ionization sources. Electrospray puts on protons. MALDI puts on protons. Electron ionization, one comes in, two come out. Okay? So this is what they're using on CSI when they test, and there's the guy on the ground, and they put it in the mass spectrometer. Then the molecule in 3 dimensions spins up that they identified. That's what they're using. The funny thing is, it's really true. The funny thing is, it is exactly like that, except that the molecule doesn't spin in 3 dimensions. When I teach a mass spec lab, I went to the trouble of getting a class 4 license from the DEA. So I have heroin and cocaine and steroids and all these things, which are really pure and good. So, kidding. And I spike them into the student. I'm kidding, jeez. A professor wouldn't last long as a heroin addict, right? Plus, I'd be skinnier. Maybe I should try it. So anyway, I would spike it into the students' samples, and then they're analyzing their samples, and heroin comes up. I'm like, what were you doing? This thing's really sensitive. And just it's the most fun I get to have with the students. Okay, so the mass analyzers, there really are only 4 of these. The magnetic sector is really historically important, and that's what I showed you that was being used for uranium purification. It was the first mass spectrometer. Very great, but just low upper mass limit. Quadrupoles, time of flights, and FTs. And everything is a combination of these. These are usually together in hybrid, okay? And you see certain advantages. That's all I'm going to say about that. Okay, we should all know this, but only charged particles are analyzed in a mass spectrometer. And this is all a mass spec can do, and this will really help you if you remember it this way. They can weigh things. That's obviously, right? They can purify things and do that very well. You can purify an isotope, not just your compound, but you can purify an isotope of your compound, an isotopolog. They can weigh, they can purify, they can break things, or you can do reactions in the gas phase. And now you can determine collisional cross sections pretty well, so you get a good idea of the folding. So there's a lot. Those are useful things, but that's it. And so if you're talking about MS, we've all heard of that. Well, if you're doing MS, or MS to the 3, you're weighing everything, you're purifying one thing, you're breaking that thing, you're weighing the fragments, you're purifying one fragment, you're breaking that fragment, you're weighing it. That was MS2, or that's MS3. Did I break 2 fragments? Okay. Yeah, good. All right. Yeah. Okay, so here's some more interesting things you can do with metalloproteins. So I think this is myoglobin, and if I told you that this was folded and this was unfolded, that's a pretty simple. These are just charge state distributions, and so the thing with a smaller cross section doesn't take on as many protons during ionization, and you get something like this. And some of these charges are coming from your metals, right? So 3 of them, in fact, or 2, depending on what they analyzed. And so you can do this. You can purify your protein, and the part that is apo will look like this, and the part that isn't will look like that. So it'll give you a really good handle, and also let you see metals that are bound that maybe you'll miss with ICP-MS. Okay? So it's nice. So it's a good little folding assay. So we know about hemochromatosis. Ferritin and transferrin are important. And I wanted to show you this mass spectrum because people have been asking me, what can you do with complexes? Well, the answer is a lot. If you take 8,000 and multiply it by 62, you're approaching the megadaltons, right? I didn't actually do that math. Let me see. Oh, you're over a megadalton. So this is big, million Dalton complexes. Now here they're seeing both ferritin and transferrin and complexes, multimers of these. And look at that, and that's where all your iron is. I love this thing. Ugh. Little ball of rust with protein around it. So you can do really large complexes, but I really want to point out, you can't lose sight of the fact, if you look at something like transferrin, it's also a glycoprotein. And those are just as important for its function as anything we look at. They're critical. And even, this is a deconvoluted mass spectrum. Sorry, that doesn't show up well, but there's your mass spectrum. And when you give people cisplatin, the off-target effect is there binding transferrin. So it's a target for off-target effects, and it's a glycoprotein, and these are things that you need another technique than maybe the one you're using just to focus on the iron. Okay, here's some other things you can do. This is really a complex spectrum, but this is a protein that I purified it from a person's brain. This is, well, don't worry, they didn't mind. 11, 10, 9, 8, 7, these are our charge states. And I know that this is rough, but picture this charge state here. I'm expanding it so you can see that there's protein, by this is fully metallated with copper and zinc. There's a normal protein and there's a protein with an oxidative modification. Over here, there's the normal copper zinc protein and the same protein with a modification. You can add deuterium to this and all at once just let them fight it out and find out about their dynamics. And in something that causes disease, that's really important. More dynamic things tend to aggregate more and this sort of thing. So check this out. Right away, what we were surprised to see is even the APO has two conformations. Probably a cis-trans proline isomerization, but we haven't got to it exactly yet. And when you oxidize it, it really affects the dynamics. Okay, so that was interesting. Now, what about if you remove the metals? Well, once you remove the metals, you can't really do I guess you could do it on the ones that are in the solution. Hey, they're hexaquo. Cool. But anyway, if you take the protein with its metals and you pop out the metals and then do global HT exchange, look at the massive difference. Look how much the metals, influence the structure, which is great. And something that causes a disease has an even more profound effect on the structure once the metals are removed. We can break these proteins. These are actual fragments, and these are HT exchange rates that don't show up there, but blue is very little exchange and red is a lot. So we can break these with thermionic electrons, almost residue by residue, into the middle of the protein and find out actually where these changes are occurring. Okay? I'm just showing you, again, now it's possible to do MS on an intact protein. And if you're interested, we teamed up with the people who make Mascot, which is the most popular database search for proteomics. And we just had them change a few things and published here what's now called Big Mascot, so that you can just use this popular search engine to search your top-down data. And talk to me if you really want to do this kind of thing. But again, make sure to use thermionic electrons, like electron capture dissociation. These are less than an EV or ETD. And if you do that, you can actually maintain your metal in your protein while you're breaking it, so you can keep the pieces if you had any question about maybe a mystery ligand.
Do you reduce the metals while you do that?
You obviously, with an EV, you can. And I would think that you would. Honestly, we've never done that experiment just to what I usually do. You could do it. But I haven't yet. Yeah. Most of the time, I'll be honest, I'm more worried about the parts that, it's ironic, and I'm sad to say this, but the parts that aren't around the metal, because I find other parts that are unfolded, the parts around the metal are always like, we got this, it's good. Okay, so just to say that you can tell the difference between a monomer and a dimer really easily by mass spec, and so all of our own studies led us to this conclusion that we could find oxidation-prone residues at a dimer interface. And when they're oxidized, you have dimer dissociation, and this is one of the first stages in disease, actually, one of the first things that happens in ALS by a lot of other groups' estimation as well. And so we started out by putting in DTME, bridging that, so it goes here between these two cysteines, assayed by mass spec, and this was to our knowledge, this is the most anyone had ever stabilized a protein that way anyhow. We could take something that was unfolded, this causes ALS, it was unfolding even at body temperature, stabilize it with DTME or BMOE, and get it to increase by 30 degrees. And then if we add back the metals, it really gets stable. These are thermal denaturation curves of a sort. I can talk about that later, but fluorophore assay. And importantly, it gained back activity. And since then, I'm just going to say that, of course, maleimide isn't something you're going to use for a therapy. We've developed cyclic disulfides and just got the patent approved for these. And cyclic disulfides go in there and bridge the two Cysteines just like this. And I tried some of the cyclic disulfides myself with IRB approval. It wasn't bad. Okay. So, anaerobic purification avoids, I only tried one for the record, and it's totally innocuous. People use it like all the time. All right. So anaerobic purification avoids artifacts. I just want to show you this. So here's an example of something you want to watch out for. I'm purifying from humans with the antibodies that I'd made, SOD, and we kept seeing this other peak. And we gathered really quickly that it was a cysteine modification. Now, this is a human brain, a human spinal cord. These are just the raw data. These are deconvoluted data. They're all the data packed together. Obviously, it looks a little nicer. Here's where the modification was. We solved the crystal structure of this, published a paper in biochemistry about that as well. But the point is that, wow, we have these neat modifications. They're in humans and not in mice. But being a guy who spent his PhD in the glove box, I thought, there's metals and there's these phthiols. Maybe I should just try anaerobic. So we fired up a glove box, and aerobically you'd see the cysteine. Anaerobically, it really starts to go away. So it was, really an artifact of the purification. Now, this S-thiolation is very interesting. Cysteine, for example, or glutathione adding to another cysteine. For years, because people had been looking under the lamppost of their proteomics experiment, which always start with reduction, which removes that S-thiolation, and alkylation, which prevents it from ever happening, it's so abundant. And now that people are doing top-down, we're seeing it everywhere. But we just have to be careful because you see it even more places than it really is. Okay? So, with that, I'll take a 2-second Diet Pepsi break. Diet Pepsi. I just got $3 for that. All right, here's the hogwash part of the talk. So I made this just for you guys, and it's not in the Dropbox. I'm not sure I'm going to put it there. Okay, so this is just because it's enormous. I have videos and things. It's pretty funny. Okay, check this out. So this is mass resolving power. Resolving power is just the mass, or the m over z that you're measuring, divided by the full width at half height. Okay, simple. That's our definition. Many others as well. It's unitless. Yes? Okay. The first mass spectrometers that were made could do this. And in the last 2 weeks, not even kidding, in the last 2 weeks, I've watched this jump in order of magnitude in my own lab, or in equipment that I'm soon to have that I used at Bruker. So you got to wonder at some point, you're seeing all this, what can you do with all this resolving power? That's the question. This is cool. Mass spectrometers have known about this for a long time, and physicists as well. This is of course this is cut off, but this is a mass defect, and look at the periodicity it shows. And so, in other words, carbon should be, by definition, 12.00, and other things will weigh more or less than carbon due to the relativistic, so they have less or more nuclear binding energy, and equals mc squared, so you can back calculate to mass, and this is what we're seeing. So this is cool, and notice the stuff you make bombs out of have positive mass defects. Right? I mean, that's exactly the energy you're harnessing. And interestingly, only 0.1% of it or less. Okay? And, that was the periodicity, and of course, just with size, there are trends as well. So this is same thing as the other. Now, I want you to think about this with me for a minute. You just go with me for these 2 slides. I have a reason for doing it. We need to start thinking about equals mc squared, because the question is, we have this mass resolving power. What's our energy resolving power? Okay? So I did these calculations. I didn't take them off of the web. So if they're wrong, it's entirely Katie, my graduate student's fault. Because she didn't tell me right now that they're wrong. Okay. Sorry, Katie. Okay, so 1 kilogram, if you could convert a kilogram of mass into energy, you could put 6,000 of these ships into orbit with just that. Okay? Equals mc squared we don't think a lot about, but it is profound. C squared is one hell of a proportionality constant. But that's still too much. Your brain, you can't imagine. You couldn't even believe your protein was modified. So, of course, you can't imagine those 6,000 cruisers. So, I'm going to help you a little bit. This, if I had a pill, a little 100 milligram pill, okay? Just one. 100 milligrams. This is the power it has. Check it out. Oh yeah, imagine. Rocket ship. This is Saturn V, and this is the one that had the largest payload ever. I chose that one. And it sent enough fuel to send another ship to the moon and back. So this isn't just your average spaceship. But the pill wouldn't just do that. It does 50 of those. Okay? So equals that, I mean, what a proportionality constant. Now, if you don't like equations, I've put this in graphical terms. The way I have to look at it, because I'm on the losing end of this as the mass guy, right? A ton of energy, a giga electron volt, becomes a proton. Okay? So I see it like this. I don't know if you see this here. Do you see that? Equals a spaceship in terms of the energy. So the energy expended to do a moon mission is the equivalent in mass, literally, of a human hair of 15 centimeters. Okay? And I did these calculations, so if they're wrong, Katie's fault. They're not. I mean, these are not wrong. I mean, is that not crazy? So basically, this is my way of getting out of doing great things with energy mass conversion. Don't expect much, but we can still think about it. Okay? All right. Here's a quick thing, credit to NC State. This is our experiment, the mass spec experiment. Kilovolts, spray. At this point, desolvation begins. Ionization occurs as protons from the acid you put in, usually attached to your protein. There they are. Now they're going to exit this, and they're going to enter quickly a region of hypersonic expansion. That's the cone. Boom. They just went hypersonic. They lost their remaining waters. We trap them. If you want to, you can react them, or you can just send them down. For example, you could break them. We send them down to the ion cyclotron resonance cell. And with an azimuthal electric field, excite them. Okay? Not only excite them, but put them in phase. They were not in phase, but now we put them spatial temporal phase, so that they can create an image current when we stop exciting them. Now, if you haven't noticed, if you're an NMR person, you're thinking, this sounds oddly familiar, and some EPR people as well. And of course, that's true. You get an image current, which you can imagine what you do with that. So there's your image current. Fourier transform that. Frequency domain, just with a really easy calculation, get that into the mass domain. That's the experiment, okay? So now that you understand that, in my last 10 minutes, I'll give you a quick run-through of some of the new things we can do with all this resolving power. Okay, one of the first things we did was, this is what the data used to look like. And this isn't higher resolving power, they're artifactual peaks. So at low magnetic fields, we just saw a lot of peaks. And there's a great theory behind this, and I'm not going to go into it in 10 minutes, but basically, just look at the data, okay? Same exact sample, and finally at 9.4 Tesla, we can start to believe, because how do you believe that this peak split if your data looks like this, right? You're not going to see a lot of peak splitting. So we got to the point here, I did this before buying a magnet. So we had the 9.4 Tesla, and what's interesting, we even saw second and third order effects of magnetic field on performance metrics, including resolution. So now that we've, as a field, moved to a 21 Tesla magnet finally, remember, we're going to always be behind NMR in terms of magnet field strength because our bore is like that and their bore is smaller. Okay, so we have, it's an engineering problem. Now, armed with just magnetic field and hope, after about 3 days, we analyzed substance P, and you normally, in a mass spectrum, would just see these 3 peaks or these 4 peaks. But if you get 1.6 million resolving power, now you can do elemental analysis. Because sulfur-34 isotope added to this has a different mass than a carbon-13 isotope, and so with oxygen and nitrogen, okay? And this is called isotopic fine structure, useful right away because we know the elements that are present, also useful because it can be used as a fingerprint, and so on. Okay. This just happened, and we just had this installed this year. what I want to point out is instead of, I'll show you, actually I'll just show you a picture here and then go back. This is what we always had, this infinity cell. It looked like somebody just took a beer can and put a hole in it. And this is what we have now. And basically this is a shimmed cell, okay? It's just shimmed to have a perfectly quadratic electric field, and let's not worry about why else. But what it does, among other things, is take data that would look like either this or this, depending on, so that's a peak and that's a peak, and as soon as you turn it on at low voltage, you see an improvement. Turn it on at higher voltage, you see even more improvement. So, and then look what it does to our peaks. They go from being like this to being like this. So it probably increased our upper resolving power tenfold overnight. Great. Okay, and then, without any hope or any trying, you just push the button, and there goes substance P. This is the kind of peak you'd see on a QTOF at 12,000 resolving power. So you wouldn't see any of this. But you get 75,000, you see the fine structure. We could deuterate this, and then look at this. In the fine structure, this is a blow up of just this peak, and then even a further blow up. So blow up the M+2, and now you can even see where deuterons have exchanged with hydrogen. Okay? And this has always been there under the peaks, but just never been resolved. It's in every HD exchange experiment. It really looks like that. Okay? It's just more of the same. We wrote a program, QDEX, and published this to be able to actually do something with the data. So I actually have to go back and modify our fit lines but basically the data gets fit extremely well, just like you would by hand, and it all makes sense. And so finally, here would be the M. So this is the monoisotopic peak, and you start adding deuterium. This is the M+1, M+2, M+3, M+4. They're all fit, and they're fit pretty well, M+5, and so on. Okay? So that's some of the things we can do. Then, 2 weeks ago, I had my first crack at this. You saw in the illustration that we were using just 2 of our plates. And the reason you do that is because we have about a billion-fold difference in current between our excitation pulse and our detection pulse. And so we have, the ring down time is just too long to use that really effectively as a, but technology improves, and so finally it isn't too long anymore. And so we started using excitation plates as also as detection plates, and so immediately our frequency doubled of measurement, therefore resolution went up. And it's relatively simple, but just a twofold increase, and it's amazingly, it works exactly like it's supposed to. It's exactly twofold increase. It's cool. So, you have a tenfold increase, you get to the right magnetic field, you get a dynamically compensated, cell, 2 omega detection. Now, a dirty little secret about FTMS is that we do not know our phase angles. And I don't have time to get into it right now, but maybe if people ask me a question, I'll tell you. But we don't know, and we have good reasons for not knowing. And so we have to do we've always been in the regime of magnitude Fourier transform. Okay? In other words, splitting the FT into a phase and a magnitude part and just going with this. And the problem here is if you square your absorption and your dispersion and add them together, they're phase shifted. And so your peak is now double. It's what it would have been. So you pay a price for not knowing this. And many people in here understand this. So what we've done, and we is not me, this is royal we, some of the people I work with, is to realize, okay, what we do is we accelerate when we excite our atoms or molecules in the ICR cell, we're doing a frequency sweep. And we're starting with low frequency and going into high frequency. So essentially we're accelerating the frequency. So any given frequency progresses linearly with time, but frequency space is accelerating. So it follows the quadratic phase equation. We know this, and so what you can do is use machine learning, a genetic algorithm, to go in there iteratively, point by point, and there's 16 or 64 million points in our high-res spectra, and optimize these for the magnitude of the absorption mode. Okay? And so you can iteratively solve this quadratic phase equation. This has been in the last year, and I tried this for the first time last week too. And it doubles our resolution, our resolving power. It's incredible. So now that this is what this jump has been. I mean, I'm not kidding, in the last 6 months, I've seen, my resolving power go up almost by 2 orders of magnitude. And that brings us into the kilo electron volt range as of today with large molecules. Okay? So certainly not EV, nothing great, but it's a start. And I should say the splittings you were looking at in the isotopic fine structure, those splittings are on the MeV range. Okay? So, okay. Now, I'm going to show you this. And Stefan, you can stop your email now because this one was for you, just in case you're asked. All right? So, check this out. This is a cyclotron. This is carbon monoxide. Low temperature. And you're seeing, by cyclotron differences alone, the quantum states. Those are rotational. Okay? And this is just room temperature. This is not a mass spectrum, obviously. This is a room temperature rotational spectrum. And of course, this is where we're talking about five. So this is on the order of 5 wave numbers. Okay? And that's by mass. There's some interesting tricks that went into doing that, but nonetheless, it happened. And I'd also like to, so just a second. So then so there's your mass resolving and your energy. And that's a specially made instrument that they used, okay? But it's the same operational principles as mine. And there they are, okay? So it can be done. And I love to just look at that and think of how, how we might apply that ourselves. And right on time, I'll say this. You can also thank, somebody with a cyclotron for your 12-digit accuracy of G value, okay? Of G. So just so you know. And this is, these are the data that got to, it's kind of incredible. And you can watch through the years. 1987, that's where G was. 2006, 2008, okay? So with that, thank you, and I'll take any questions.
Thanks, Jeff. Are there any questions? Everyone's speechless.
Oh, that's the worst feeling.
Everyone knows that that the questions can be asked best with you over a beer, and that you can handle many questions. Well, then, I think we probably should move on to the next talk. Nikolai is already coming down to set up. The next talk will be on a method that we have not covered here at our workshop before. It is a little bit more of a unusual spectroscopic method. It combines vibrational spectroscopy with Mössbauer spectroscopy. The acronym is NRVS, nervous. And Nikolai is, of course, a workshop veteran. He has given talks on MCD spectroscopy in previous years, and at this workshop does the MCD tutorial. And this year he's going to tell us about the technique that he also does. Nervous.
Should be. Oh, power is over here. Guys, ask some more questions. I'm not done yet.
More questions. I just give the mic over to Jeff so he can... Can you please get this to work, Nikolai?
Come on. No. This. Well, I plugged it in with my connector.
Is that HDMI? Or
Yeah.
Take it way down. I'm not sure what the issue is.
Let's just try unplugging and putting it back in. That was last time.
Okay.
So it might be the result, or
You might have it on extended. You need to put it on mirroring.
I mean, it works with the simple projector upstairs, right, that we used for MCD. So it is a bit odd.
Well, it also could be your
Like function F8?
I mean, it's trying to, right?
trying.
It's trying.
right.
And then it gives up.
Can we do we have one version up, or can we use Dropbox?
No, I have
It's
to.
going out. It's going out. It's just not going here. Where's your?
Yeah, do you have like an FNF8 or something?
Yeah. Where's your?
Let's see this.
What happens if you try full screen mode?
Let's see. So it should be this one here, but it does not do anything. No. Well, I guess I can put it on a memory stick, and we can use that computer. That's weird, though. It never happened.
Was it the same presentation, Nikolai?
No, not quite. So I can transfer it. All right.
It's doing something. There we go. We're good.
Ah, all right. The magic just happened. All right, sorry for the delay, just some problems with technology. I have to say this was a really entertaining mass spec talk, probably the only one that didn't put me to sleep.
That's the nicest
But-
thing you've ever said in 20 years.
But now, what am I going to do now, man? There's nothing I can do again now. Maybe we should just go to the bar now, because how are you going to follow up on this, right? All right, so I'm going to tell you about nuclear resonance vibrational spectroscopy. Carsten gave me 45 minutes, so I'm not going to dwell too much into the theory and massive amount of equations we could put up here, but I'm going to talk more about applications, what we can do with this. Here's a picture of cytochrome C. This is one of the proteins we studied in collaboration with Kara Brand. And then here we get the nerve spectrum, which is here in black. And then we do some DFT, and you see, well, it doesn't fit what's usually the case, but then we can refine from there. I'm going to talk about how we do this and some other examples. All right, so NRVS is a synchrotron-based vibrational technique that kind of really come to fruition in the 1990s, because we need the equipment to be able to do this. People had thought about this already earlier, but as you see in a second, since we need a synchrotron and it has to be a special synchrotron, it's not an experiment that can be done easily, right? And so it's really then, it started in the 2000s then that the technique really took off, and if you look at the papers being published, really more and more than was coming in the early 2000s. And it is a combination of nuclear excitation and molecular vibration. So it's kind of a acute effect, right? I mean, you guys are all now familiar with resonance Raman. So in resonance Raman, we excite, right, our electronic transitions, and then we observe inelastic scattering in resonance of these electronic transitions. So this is the normal Raman effect. And so here now we go and do nuclear excitation. So we excite a nuclear transition, and then we measure inelastic scattering in resonance with that nuclear transition. And it's mostly done with iron 57, although you can also do it with other Mersbohr active nuclei, like tin, for example. There's some tin NRVS papers. But really it's mostly done with iron. And then in the case of iron, right, you're looking at the Mersbohr line. So this is the connection to Mersbohr. You excite the Mersbohr line and measure the inelastic scattering. And you'll get a complete set of vibrations that involve now the probe nucleus, which is iron in this case, iron 57. So here is, so Carsten's going to hate this. This is my, 10 cents Mersbohr version here. But we already heard the Mersbohr lecture, so I'm going to go over this really quickly. So in Mersbohr spectroscopy, right, we need a light source, especially if you want to do it in the lab, like Rudolf Mersbohr did, the guy who really got this to work. So we use iron 57 as a radioactive source, and then it decays down into cobalt 57 and an iron foil. It decays down to iron 57 in this highly excited state, and then we fall down into this lower excited nuclear state. This is the Mersbohr active state here, and you can see it's about 14.4 kiloelectron volt above the nuclear ground state. These are nuclear states, right? So 14.4 kiloelectron volt is a lot of energy. If you're used to electronic transitions, couple EVs, right? This is like, I think, 100 million wave numbers or something. You can calculate it. 14,400 times 8,065 is a pretty big number, right? So here we're down, and then we emit here the radiation. This is now the light source that was used in the classic Merce-Bohr experiment before we had the synchrotron. And that's the radiation that we need to do NRVs. This is why I'm kind of going through this. There's a purpose to this nonsense here. So then, in the classic Merce-Bohr experiment, you have the emitter, your source on one side, which is your cobalt-57 in an iron foil, and then you have your sample, your absorber. And usually the energies here are not quite in resonance, so you have to kind of find a way to tune a little bit the energy of your source here, and you can do this by the Doppler effect. And now, get this, right? We plot this usually, since we're doing this with the Doppler velocity against millimeter per second. 1 millimeter per second is 10 to the minus 4 wave numbers. The line width of this is not insane, right? We're talking about 100 million wave numbers energy, and we're resolving 10 to the minus 4. But that's because it's a nuclear transition that in the greater scheme of things isn't really influenced very much by what's going on at the electronic shell. It doesn't really care about it at all. It cares about it 10 to the minus 4. That's about how it cares about what happens in the electronic shell around it, right? Compared to 100 million wave numbers for the energy. This is about how much it cares. So really not a whole lot. But because the line is so insanely sharp, right, we can actually resolve this. And this is, of course, why Merce-Bohr works so well. It can still show us something about the electronic environment of the ion center, despite the fact that the effect is so small. So thanks to the sharp line width, and so you get your Merce-Bohr spectrum then. And Carsten told you all about it. And so this is really all I want to say about Merce-Bohr. So this is really the 5-cent version of this. No magnetic field, no zero field splitting. But this is the stuff that we're looking at, right? So we're going to use now this energy line here to excite our iron 57 nucleus into the excited state and measure inelastic scattering. That's what we want to do in NRVs. Yes, that's not so important here. So we can also sometimes kind of draw the analogy for students. I say it's a nuclear resonance Raman, right? It's essentially inelastic scattering in resonance of a nuclear transition. And the interesting part, though, is that for one thing, selection rules are completely different here. Selection rules for resonance Raman are pretty complicated, and you have group theory and deal with all this stuff. And here it's very simple. The only kind of selection rule is that you have to have ion motion in your vibration. And in fact, the intensity that you see in your spectrum scales with the amount of ion motion. That's all it is. So it's very simple, right? And then in this sense, then when you measure your NRV spectrum, you get the complete set of motions of the probe nucleus that you're looking at. So any kind of motion that has some ion or any kind of vibration that has some ion motion in it will show up in your NRV spectrum, but nothing else. So there are some actually, of course, it's a limitation in terms of the types of vibrations you can see, but as you will see a little bit later, in terms of vibrational analysis, this is a huge plus, because this allows us to just do things that we weren't able to do before with IR and resonance Raman, because of this very simple intensity rule. So the peaks that you see then are the recall-free resonance energies. They correspond to these vibrational transitions, these sidebands relative to the main line, which in Raman we call the Rayleigh line, right? The Rayleigh emission line, where there is elastic scattering. Here this would correspond to like the Merce-Bohr line, and then we have these sidebands here. But because it's inelastic scattering, just like in resonance Raman, NRVs is also a very inefficient process. And that's really where the synchrotron comes in, right? So with like your Merce-Bohr source, anything that doesn't work is way too inefficient. You get no intensity at all. So you need to be able to blast your sample here. And there are not many light sources, not many light bulbs that are strong enough to allow you to do this. Right? And actually, there's really only, I think right now, 4 places in the world where you can do this experiment. Here, this is Agar National Lab. This is the advanced photon source. This is where we usually go. So this is the place in the US where you can do this experiment. And for us, since I'm from Michigan, this is kind of cool because we can drive there about 4 hours. So for us, it's easy access to go to Agar and do the experiment there. And there's a beamline in France and Japan, and I think there's one in Germany now where you can do the NRVs experiment. So access is still a problem to this technique because you got to get beam time at one of these synchrotrons, and that can sometimes be tricky. So here's just a little overview to kind of give you a feel for how this works, the setup works. This is kind of a cartoon here of the NRVs beamline at Agar National Lab, where you start off, of course, with the accelerator, which produces the the broadband X-ray, gamma ray vibration. And so you got to go in now, and out of all these photons, you got to cut out the ones that you want, 14.413 kilo electron volts for our Mössbauer transition. So we go over this in more details. A couple of monochromators here, where you kind of throw 99.9999% of your light, you all throw this all away in order to get your bandwidth down. Because remember, we want to resolve now vibrations. And at Agar National Lab, the resolution that you get is about 7 to 8 wave numbers, which is good. You can do stuff. If this was not great, could be better. But that requires essentially that you get down to your like a line width, right, of your excitation beam that's in the milli-electron volt range, right? So you got to really have good monochromators. And again, whenever you monochromize something, that means you throw stuff away that's not quite right? So you kind of start with this pool of photons, and you narrow it down to this tiny little bit that you use. And so if you want to make advances at this, you need a stronger synchrotron, produce even more photons, get more down to your sample, then your measurement time will go down, and your resolution can go up, and so on, and so on. And so these are things that are currently, actually people work on in Argonne. They just put in a proposal to increase intensity, get down resolution to, I think, 2 or 3 wave numbers, and would bring down the measurement time. So there are some things coming that could really help. And then if you don't need that much time anymore to measure your spectrum, more people can get access, and so it looks like there's going to be some improvements. So if you look at these components here, so there was a lot of development that went into this in the 90s when this beamline was built. Right, so the first component is what they call a heat load monochromator, and that's because that's where most of the photons are thrown away, because you go down now to a line shape here, bandwidth of 1 electron volt. And so this monochromator is composed of 2 crystals. You can see I have it listed here. It has to be very well cooled. It gets really hot, and then here you get your beam down to a few electron volts. So this is the heat load monochromator, and then there's a second one right after it, which is the high-resolution monochromator. And this one here, this is the part where you essentially have to build a new one for every single Mössbauer line, or every single excitation line you want to use, you have to build a new monochromator. So if you say, okay, I'm not interested in iron, I want to do tin nerves, then you got to go build a new high-resolution monochromator where you can now get the right energy now for the tin nuclear transition, and so on. So every time you want to change the nucleus, you actually have to build a new beamline in that regard, right? So this is also a bit of a problem here in terms of using this technique more broadly for other Mössbauer elements. But as I said, there are a couple of papers out there where people do tin nerves. So here, this is a specific silicon crystal cut at a specific angle. They explained this to me once at Argonne. It was very, very difficult to make. They had to make a bunch of them and throw most of them away, and then finally they got the right one that works. And now you get down to about 1 milli-electron volt, and now we're talking about vibrational resolution, where you can actually resolve different vibrations, right? So now we're down here where we can do the experiment. And so then, let's see. So next step then is from here we go to the sample. So the way the beamline is built, the beam comes in and grazes the sample here at an angle of about 6 degrees. The detector then is in 90 degrees, so we're detecting 90-degree scattering, and that is done for a practical reason because there's a lot of elastic scattering that comes off 180 degrees from the sample. So we lose all this. We don't want to measure this anyways, and so and then we measure here. This is essentially just a photodiode. The detector just counts photons, like in the good old Raman spectrometer before you got the CCD camera, right? You just count photons. And this is this piece here. Okay, so here is a picture. This is from a review here by Tim Sage and Bob Scheid, and they're one of the kind of pioneers in the sense of the kind of really first people in the broader area of bioinorganic chemistry started using this technique and published a bunch of papers in the early 2000s that really kind of got people's attention for this technique in the bioinorganic community. And that's also how I essentially got into this, right? By looking at this and saying, wow, this is a pretty cool experiment. Let's see if we can do it. So if you look at this, so this is here plotted against just counts, so just the spectrum, how you measure it. Here's your frequency now. We kind of set the 0 here to in Raman, this would be the Rayleigh line, but here we can say this is the Mössbauer line, right? So this is the elastic scattering that's observed. And then again, this is the major effect that you, oh, question.
How do you get
Well, so in the detector, you can scan with the monochromator then.
Oh, okay. So you're scanning
Yeah,
the incident beam?
You're scanning with the incident beam, yeah. You don't scan on the detector side. There you just count photons, so you scan with the incident beam. And so, yeah, every time you run your spectrum, you have to align first. Then you take a spectrum, then you realign, and so on and so on. So here you can see the sidebands here, hardly noticeable, but then when you kind of enlarge this by a factor of 30, then you can see here, these are actually now vibrational sidebands like in a Raman spectrum. Right? And then you can take this, the raw intensity, convert this over in the vibrational density of states, and this is something that's really useful because it has this really, really simple intensity relationship, and so this is really what we like to look at. And we'll get there in a second. And then you can do the typical things you can do with Raman spectroscopy. So you can measure Stokes and anti-Stokes here. You can use this to calculate sample temperature if you wish to do so. Usually people don't do this, but you could if you want to. So the typical things you could do with a Raman spectrum, you can do here too. So it's really an analogous effect in that regard. But the origin, of course, the physical origin coming from a nuclear excitation is different. Right? So again, it's a very different selection rule. To be honest, I don't know. I will have to look this up, what this is. So we're going to do a couple of examples, and as we do a couple of examples, we kind of zoom a little bit more into the theory, a few equations only, and then talk about, of course, looking at spectra and how we can apply this and how we can connect this now to vibrational analysis. And that's really one of the big advantages of this technique, right? So here's just one thing that we've been working on in the past extensively is looking at NO binding to ferrous hemes. You can do this with myoglobin, for example, and there are some interesting questions here, like, for example, the effect of the proximal ligand, whether the complex is 5 or 6 coordinate, what's the effect here of this axial histidine donor. You can look at the effect of hydrogen bonds, and one way to look at this, of course, is then by detecting vibrations here, NO stretching frequency, I and N, and analyzing them and see what's the difference, right, with or without. I can mutate out the hydrogen bonds, what happens, and I can look at this. I can also compare this to model complexes. I'm going to show some data for this tetraphenylporphyrin type model system, and again, you can make this 5 or 6 coordinates. Of course, here you don't have hydrogen bonding, so you also have a way to compare this in this way. And so from vibrational spectroscopy, of course, right, we can get all kinds of information. We can get information about vibrational frequencies, force constant, bond strength, and then especially if you compare two things without hydrogen bonds, without the 6th ligand, you can compare the force constant. You can actually see how electronic structure, how bonding changes, right, in a really direct way because it's reflected in these vibrational frequencies. And so if we want to get information about these heme nitrile seals, we want to know about ion-NO bonding, then of course you want to look at the NO stretching frequencies, where nitrogen oxygen are stretching. That you can detect pretty easily with other techniques. You want to look at the ion-nitrogen stretching frequency. You can see, there the ion is going to be moving, so this is going to be nerves active. So this is one where we can get into this. And then we have this about 140-degree angle here, which is really unfortunate because that means that the ion-nitrogen stretching mode also has the potential to mix with the corresponding bending mode, right? And so now we have mode mixing. That means we also have to do some vibrational analysis and really to deconvolute that and look at force constants to see how bonding really changes because of this effect. So we got to look at all three of these vibrations and then analyze from there. And for the corresponding 5-coordinate complexes, so there's nothing bound here. This is relatively straightforward, and in resonance Raman spectroscopy, you can really see all the relevant vibrations. Then you're good, you don't need nerves, but nerves, of course, always comes to the rescue when things get difficult, right? And especially here, since our intensity really depends on the amount of ion motion in a vibration, any kind of metal ligand vibration, right, it's going to be nicely visible by nerves. And it's not necessarily a Raman active mode, but nerves can see everything, again, where ion is moving. Right? So metal ligand vibrations, this is really the strength of nerves, to look into those. But if you're interested in electronic structure, small molecule activation, that's what you really want to know. How does bonding change? So these are the vibrations you really want to look at. Right? So we're going to look at 6-coordinate complexes here because, as I said, the 5-coordinate ones are relatively straightforward to analyze. So here is a nerve spectrum of, let's go back. of the, where's here? This guy here, right? This complex. Tetraphenylporphyrin, 1-methylmidazole, NO. Here we go, and here are our raw intensity, our counts, and here's what the spectrum looks like. So you can see there's a bunch of cool peaks here that we can find in the spectrum. And then, of course, we can do the usual thing in vibrational spectroscopy is isotope labeling, increase the mass, frequency will go down. That will allow us to see things. And we'll see is, okay, where are vibrations where nitrogen or oxygen are moving, right? And you immediately identify two in this spectrum. One is here at around 440 wave numbers, and the other one is at 563 wave numbers. And then, of course, the big question is, what is the assignment for those? And another question is, what is all this other stuff? And, of course, most of these vibrations here will be ones that involve the ion and the porphyrin. Right? There's a lot of vibrations between the ion and the heme macrocycle, so most of these vibrations here belong to ion-porphyrin vibrations. Oops, that was too fast. So what we do then is, usually we don't look at the raw intensity spectrum here, the counts, we convert this over to the vibrational density of states, which is a two-step process where first the recall-less line, the Mössbauer line is subtracted out, and then it's converted over to the vibrational density of states. And the real advantage is, look at this beautiful equation, right? This is the vibrational density of states. There's only two things in there. There is this amplitude factor, which directly relates to the amount of ion motion in a vibration, and there's a line shape. So we can just take the spectrum then, and if we have it in the vibrational density of states, you can integrate a feature there, and you get the E squared, the amplitude factor. Right? You can also do it directionally. You can ask the question, does ion move in X, Y, or Z direction? So we can project out X, Y, or Z direction, doing it this way, and then we can determine, okay, we're moving mostly in X, mostly in Y, mostly in Z direction, and so on. So hidden in there is directional information, how the ion moves in your molecule. That's also pretty powerful. Right? So if we can say something about this, that will allow you to assign vibrations also. If you know, oh, is the ion moving in the plane of the heme? Is it moving out of the plane of the heme? That tells us something, right? What's going on? And so as I said, it's going to be light on the theory, but here, this is a classic here. This paper, if you want to read the theory, if you love equations, you want to see lots of them, look up this paper. It's a really cool paper, but it would take me like 45 minutes just to go through like half of this. So I said, well, we're just not going to do this, or just keep it application-based. So these amplitude factors here, these E square factors now, have a straight relationship. I'll get back to this in a second when we'll talk about vibrational analysis, but you can see there's the mass of the ion in there, and there's some kind of displacement factor in there. So you can actually calculate these amplitude factors straightforwardly from a frequency calculation. So you do a DFT calculation or normal coordinate analysis, and you can calculate these amplitude factors. And imagine this step forward, right? If you do a vibrational analysis like a normal coordinate analysis, you cannot calculate IR intensities, and you cannot, to save your life, calculate resonance Raman intensities. And even if you do DFT, you can calculate maybe IR intensities okay, but resonance Raman intensities are a huge challenge, right? So when you do vibrational analysis, normally what you do is you simulate the vibrational energy, and you simulate a bunch of isotope shifts. But now we can actually simulate spectral intensity. And I mean, that gives you a whole another order of magnitude in terms of confidence level about your simulation, when you can actually simulate now your spectral intensities. And then on top of this, if you have information like this, you could even simulate the directionality of your motion if you have information about this. You don't get this from a powder spectrum, of course, but if you I'll show you some single crystal data, you can actually get to this. Right? And so this really opens up, this opens up to a whole new dimension of what you can do with like vibrational analysis, and how you can build your confidence level in your simulation. Here's a couple of other things. Right? In the harmonic force field, we also have these cool relationships here that are fulfilled. So if we're looking at the amplitude vectors for the ion, and then we sum them up over all vibrations and rotation and translation, all movements of ion, you sum them all up, the total is free. So you can move one time in X, one time in Y, one time in Z direction, you normalize to free. So that's pretty cool. And if you look at one vibration and you sum up the E square factors over all the different atoms in there, that will always add up to 1. So all these are really cool normalizations in here, right? So that's why we love the vibrational density of states, because of this very simple relationship here of the intensity to the amplitude factors, which are then very straightforwardly calculated. So then this is the spectrum now that we saw before, transformed over in the vibrational density of states. Now we can take this first band here, the 437. If you just integrate it, it gives you the E square factor for the ion. And then there was this other isotope-sensitive band. We can do this too. So we can simulate now, as I said, with normal coordinate analysis or with DFT, you can calculate these intensities straightforwardly, and you can use them to restrict simulations. Also here, right, we could look at the ratio. What's the ratio of intensities here between these peaks? It's about 0.5. We can use this as a constraint. When we do our normal coordinate analysis, we say, okay, this has to be like this, right? And so, as I said, this is just fantastic from this point of view. So here is the next step then, is a single crystal. So we don't always do this, but this is the way now to get this directional information. I think Bob Scheid was the first one who started doing this at Agar, and he was probably heavily involved when they added this the setup to the beamline where you could mount your single crystal and rotate them properly and do all this cool stuff. Right? So what we can do now is, since the beam that comes from the synchrotron is linearly polarized just in itself, we can now mount our crystal, for example, in a way where the plane of the heme is parallel here to the oscillation direction of the electric field in your gamma radiation. And in this case now, you only get scattering from vibrations where the ion moves in the plane of the heme, and that gives you that blue spectrum here. And then you rotate your crystal, and now you mount it in a way, right, that we're perpendicular to this oscillation direction. Now we can only get scattering from vibrations where the ion moves orthogonal to the plane of the heme. And so we end up getting that spectrum in blue and that spectrum in red. Right? And so out of plane, of course, this is interesting. Right? This is where things happen. If you have an ion complex with a heme, the 4 positions in the plane are blocked by the heme, so there's never anything happening there. All the chemistry happens in the axial position, so we want to know what's going on there. Right? And in this model complex, remember, we have the NO on one side and the 1-methylimidazole on the other side. So now if you look at vibrations that are heavily red, those are ones where ion moves out of the plane. So here's this one at 150 wave numbers. This is the ion imidazole stretch. Really low in energy. This is a reflection of the trans effect of NO. And then you can see this 440 wave number band is almost exclusively out of plane polarized. So the ion just moves out of the plane of the heme. That feature at 563 on the other hand has these kind of mixed polarizations. It has blue and red intensity that you can see in the spectrum. And so this is further information now that we can also use. We can, of course, simulate that very easily. Right? When we do the normal coordinate analysis, we know where the ion is moving for all these vibrations. So the first step then, when you want to analyze this, usually is doing a DFT calculations. They have become so cheap and easy to do that you can say, okay, I just run a frequency calculation, and I start with this. And so again, we've already looked at these equations, and I just wanted to point out now, kind of taking this one step further, if we look at this equation for the amplitude factor, that these IRs here, these R factors, are actually atomic displacement vectors. So you get that from normal coordinate analysis. You know the mass, and so I've already pointed this out a couple of times. Now you can calculate them. First step, you could do a DFT calculation. Then you can see if you're happy with this. If not, then you might have to do some refinement here. Here's just one example, just a little sidestep. We published a paper on this in 2010 where we looked at octa-ethyl porphyrin, this 5-coordinate complex. You have these 8 ethyl groups in the periphery of the heme, and then we looked at all these different orientations, all up, 2 up, 6 down, and so on, all possibilities, and did a bunch of DFT calculations, but I really don't want to go into this. But what you can see here is the experimental spectrum is in black, right? And then here are just 2 different flavors of DFT. One gives the one in blue, one gives the one in red. And in the meantime, people have published much more extensive studies on this, where they tried, 15 different DFT methods, and then look how they compare. But you can see overall, the agreement isn't that great, right? So you can see this is the ion end stretching band here at 522 wave numbers. And yeah, if you use the red method, you kind of hit it, but then you can see here, this is the bending mode is really off. And so at the end of the day, we usually then start off with this, and then we do some refinement, some normal coordinate refinement. So that's what we did here for the 6-coordinate complex. And this is now our simulation, right? So black is the experimental powder spectrum, orange is then the normal coordinate simulation that we were able to do, and that contains isotope shifts. It contains, of course, the intensities that you can see here. It also contains the directional information, so the single crystal spectra, right? So simulating the Z spectra and the XY spectra, everything in there. And the way we do this is we start off with the best DFT calculation we can find, and then we just refine that force field against the experimental data. And really, we only change a few force constants in this ginormous force field. One of the biggest problems in normal coordinate analysis is that you're so underdefined. There's so many force constants, so little information. So what we usually do is to start off with a DFT calculation and then do this, we call this quantum chemistry centered method, where we really just refine a handful of force constants then to simulate or to improve essentially on the DFT force field to then simulate the experimental spectrum. So this is the total spectrum here, and then we can also look at, well, these are the component spectra now that we simulated. So the Z polarized spectrum, the simulation here in red, and the XY polarized spectrum here in blue. And you can see that we can reproduce the key features here. For example, the fact that this 440 wave number feature is so strongly out-of-plane polarized, and then the mixed polarization of that feature at 563 wave numbers, and then we can kind of now identify what these porphin vibrations are. It's not so interesting for today. And here again, the ion imidazole stretch, right? So we can really kind of get into the nitty-gritty details here of the spectrum and analyze everything. So of course, the more you want to learn, the more work you have to put into this, as it always is. So this was a little bit of work. I think it took me about a month to simulate this. But this is a hard one because the molecule is so big, right? So we can then assign our spectra here. So we have the iron-nitrogen stretch with the strong out-of-plane polarization here, and then we have the bending mode here at 563. Now this is important, right? Because remember, if we look at the 5-coordinate complex that doesn't have the imidazole, the iron-nitrogen stretch is about 520, 530 wave numbers. So now when you bind the imidazole, is the iron-nitrogen bond going to be stronger? Then this will be the stretch, or is it going to be weaker? Then this is the stretch. So having the proper assignment here is really important to understand what's the change in electronic structure. Are we strengthening, are we weakening the bond when we're binding the imidazole? So you got to come up with the right assignment in order to draw the right conclusion. So looking at this and putting this effort into there is actually worth it, because at the end you want to know what the change in bonding is. So you got to make sure that you assign these vibrations correctly. And this has been pretty difficult if you look also at the literature, because in resonance Raman, for these 6-coordinate nitroseals, for some reason, when you do resonance Raman spectroscopy, you only see that higher energy mode, around 550, 570 wave numbers. There's essentially only one report by Kitagawa's group where they see something around 440, but it's really, really weak, so they don't really analyze it because it's a really weak feature. And it's essentially only in retrospect where you say, oh, I know it has to be there. You go back and look at the Raman data and say, oh yeah, there it is, but it's tiny. And so people usually just look at this one feature here because this is easily detected by resonance Raman spectroscopy, which you can do at home in your lab, whereas this, again, you have to get to the beamline and it's much more complicated. So we can also look at this, and then we get these little animations then, right? So you can see here, this is the iron NO stretch. You can see the iron pretty much moves up and down. Most changes in the iron-nitrogen vector. Of course, there's always some mixing of porphin vibrations. That's always the case. And then you can see this looks more like a classic bending mode where most of the motion is in the nitrogen. It kind of swings up and down, but there's some stretching character in that mode too. There's some admixture of the iron-nitrogen stretching coordinate in order to get this kind of motion. So, with this we can then go on and ask the two questions that I had up there that I posted in the beginning. So the first one is, when we compare now 5 and 6 coordinate complexes, what's the difference? We have our assignments now, but we have mixing between, right, the stretch and the band, especially these ones are pretty well separated, so their mixing is pretty small, but here they are strongly mixed, and so you can't, I mean, the iron NO stretching frequency gives us some idea that the bond gets weaker, but if you really want to quantify this, you got to get rid of that mode mixing effect, so you got to look at force constants now, which are independent of mode mixing. So you look at these numbers here, NO stretch, iron N stretch, and you can see both of these bonds become weaker when you bind the imidazole, both force constants drop. So there's a direct correlation of these bond strengths between the 5 and 6 coordinate complexes, and that tells you now that you're weakening the iron NO sigma bond, because if you mess around with the back bond, you get that famous inverse correlation, right? Where one gets stronger, one gets weaker. Both get weaker at the same time, you mess around with the sigma bond. And then you can take this further, and I don't want to go into all the details, but to just give you an idea of a bonding scheme here, right? So in these complexes, you have a low spin iron 2. So D6 low spin, you have nitric oxide with this one unpaired electron. This is kind of the overall situation. You start to make a bond between them, and remember, or maybe you have not heard about this, but in nitroseals, we always like to use this Ennemark-Feldherm notation, so I just want to make sure I drop this on the way. So these iron 2 NO complexes would be FeNO7s. We have 7 valence electrons, 6 d electrons from the iron, 1 electron from the NO and the pi star orbital, so it gives you a total count of valence electrons of 7. So we call this FeNO7. It's kind of a way to count electrons, especially since in these nitrosyl compounds, oftentimes you don't know a priori where the electrons are, and sometimes you have to work really hard to kind of figure out what is the best description of this electron distribution. And I'm going to show you an example on dinitrosyl ion complexes where this is really not straightforward. So this is the overall situation then, and then we can put them together, these orbitals, and make bonds. So we have the sigma bond between dz square and this pi star orbital, the singly occupied one, and then we have back bonding going on. And then you can imagine now, when you bind your imidazole here, NO has this big trans effect. So trans effect means that the two ligands influence each other. So when you bind the imidazole here, then you weaken the sigma bond on the iron NO side. And that's essentially the effect that you see. But of course, it goes both ways. And that, again, is something that is important in biology, because that is the famous trans effect. If you turn this around now, the way I looked at this so far is I have an NO complex. I either bind or don't bind this axial ligand, but biology does it in the other way. This is soluble guanylate cyclase, which is our mammalian NO sensor, right, enzyme. And here you have a high-spin ferrocene where the imidazole is bound. You bring in NO, it binds, and because of that trans effect, it breaks the iron-imidazole bond. Because 5-coordinate nitrosyl is a huge conformational change now in the enzyme, and that turns on the cyclase domain in the enzyme, and that's the way the signal is transduced that NO is bound. And that all goes back to this trans effect here. So this interaction, you can kind of see this here. Here's this dz square orbital. It's a little bit tilted over pi star orbital of NO. Here's the donor orbital of the imidazole, and they're kind of competing with each other in this trans effect. So this is also important for this kind of stuff. Okay, so last thing then is the thing of the hydrogen bonding. We can now go and look at myoglobin again, and as I mentioned before, when you do resonance Raman experiments, what you really measure is this bending mode between 550, 570 wave numbers, and then we can correlate this with the NO stretch. We have a diagram. Here's wild-type myoglobin. Here are mutants where the distal histidine has been removed, so the hydrogen bond is gone, and interestingly, our model complex ends up right in this area, and of course the model complex doesn't have a hydrogen bond either. So we can kind of look at this and think about what this could mean. We also have a little bit of more information because there's a paper by Sage where they measured the iron NO stretch in myoglobin, 443 wave numbers. Our model complex is 437. So you can see the hydrogen bond doesn't really do too much to the iron NO bond, yet it does something to the NO stretch, right? We go here from like 1610 to like 1630, and then it also influences the bending mode. And we think that this is probably more a polarization effect, where you polarize the pi and pi star orbitals of NO, and that causes this change in the NO stretching frequency. And that's what you observe here. But so you can use vibrational data to really think about electronic structure in detail and think about how things change in your electronic structure when you add ligands or hydrogen bonds or other types of things, right? And so the vibrational information really connects directly to electronic structure. So I think at this point we're going to go to another example. So are there any questions about this part of the story? This is kind of my main example, since we worked a lot on this. All right, everyone looks kind of happy, ready for lunch. So here are these dinitrosyl ion complexes. They're also important in nature because people think that they are a major storage pool for nitric oxide in mammalian systems. Right? So this is a way you can make them in the lab, where you start from the dinitrosyl dicarbonyl ion complex. Here you add two equivalents of a ligand, a neutral ligand, nitrogen donor ligand, and you can go to this FeNO210 compound now, right? So formally, this is an ion 0 with two NOs. That gives you a valence electron count of 10. We'll see what of this really holds. You can oxidize this, make the FeNO2 This is just a synthetic pathway. Under physiological conditions, you would expect to see this form more when you have these neutral, like nitrogen donor ligands. In biological systems, you would think histidines. And then there's also sulfur versions of this, but I'm not going to talk about this now. Otherwise, we're still going to be here tomorrow, since so much work has been done on these cysteine or sulfur-coordinated DNICs. When we looked at the ones of nitrogen coordination, we used dimethylphenanthroline to do this. Here's a crystal structure. This is this guy here, the FeNO2 complex. Nice tetrahedral compound. And then we looked at this here with Carsten. Looked at the Mössbauer parameters. That was interesting, right? So when you go from the 9 complex to the 10, then you think you would reduce the compound. At least you kind of have to add an electron to get there. But if you look at the isomer shift by Mössbauer, it actually goes more positive. So upon reduction, the ion feels more oxidized. Of course, this is a kind of a simplification. The way people use isomer shifts is a simplification, but certainly it's not what you would expect. And there's some other literature precedents for this NAC compound. That's the other compound that has been studied in much detail. It was first made by Lippert's group, and then Ye and Nase did some Mössbauer and some computational work. But you can see here the change in isomer shift is really small. So the isomer shift is very, very, very indirectly related to ion-NO bonding. Right? So looking at the isomer shifts is one thing, but if we really want to know how bonding changes, you've got to look at something that is more directly related to bonding. And this, again, would be vibrations, right? Vibrational frequencies. So we can do this with nerves. We can see, is there any difference in the vibrational fingerprint? So here's the FeNO2 compound. You can see we have two pretty strong signals in nerves, 580, 534, and then there is this one feature here at lower energy at 355. And if you compare this to the FeNO210, you can see, yes, there are ginormous differences in the vibrational data. So clearly something happens here in terms of ion-NO bonding. Right? So this guy is gone, everything else shifts up, and here we are with a huge bunch of signals, so what now? So now we're going to do the same thing as before, but I already explained all this normal chord analysis stuff. So I'm not going to bore you with this again. I just show you that we can simulate those data. This is the FeNO2 this is natural abundance, this is 15N18O. Black is the data, red is the simulation. And then we can also simulate the FeNO210. We have this interesting effect here where natural abundance, and there are two peaks here, and then when you isotope label them, they go into one, so they superimpose. So there's one feature with a large isotope shift, one with a small isotope shift. That's key here. With this information, we can assign these modes. Otherwise, it would be difficult. And so on and so on. And then we can get our assignments. And don't look at all these numbers. I'm just going to tell you what's important. So when we go from FeNO2 to 10, you can see the NO stretch goes down. On the other hand, here the ion NO stretches, symmetric and antisymmetric, they go up. So that looks like a hallmark of back bonding, right? Back bonding when you have this inverse correlation, one up, one down. So that's interesting. And then, of course, look at this guy here. That's the outer plane bend. Goes up from 355 to 545. Right? Insane. Why is that? And so we think the reason for this is, after looking at our force field, after modifying, is that just in generally, these bending modes are strongly mixed with the tetrahedral core vibration. So we have essentially nitrogen, ion, nitrogen bending modes around the ion center, and that just the whole FeN4 core just gets a lot stiffer, which means you increase bond order between the ion and the NOs. And as you increase the bond order from single bond to double bond is much harder to bend than a single bond, that you see this incredible increase in the energy of this bending mode. And then, to make a long story short, we can kind of pull this all together. So first of all, here's some insight into electronic structure. That goes back to Frank Mace's paper where they first proposed, right, that these FeNO9 and 10 complexes should be described as ion-free NO minus, ion 2, NO minus. So again, you can see very different from if you just count electrons, you see ion 0, 2 NOs, but actually looks more like this. So really, these electron distributions are really complicated. And then the Mössbauer spectroscopy, though, we see when we do this reduction, actually we're looking at a more oxidized ion. And then I've told you about all the vibrational stuff. So we see this increase in iron NO multibond character, Fe bond strength goes up, NO goes down. And so we can all relate this back to a dramatic increase in iron NO back bonding upon reduction. Right? So we put the electron on the iron, but we greatly increase the back bond, and then we suck it right back out down onto the NO ligands. And of course, if you have strongly back bonding ligands, then you see these effects where you have these very positive low, not positive, they were low isomer shifts. It's a hallmark of strong back bonding. And so I think that this all makes sense in kind of this regard, and we have direct experimental evidence for these changes from the vibrational data, right, which reflect this, and we can analyze this. And it's further supported by DFT. So if you look at DFT bonding schemes, and again, this is all complicated, and the really only interesting part here I want to point out is if you look at, so these are the I and D orbitals, right, these are high-spin ion centers. If you look at the FeNO29, you can see these are mostly really ion-based, 80, 90% ion, a little bit NO character, and then when you reduce, you can see how the NO character just goes up into these ion-based orbitals, which is a reflection of increase in back bonding. So the DFT calculation, if you look at the bonding scheme, they support also this conclusion. And that was already, of course, this was already proposed before by Frank when they published their paper in 2010. They looked at these DFT bonding schemes in much detail, but our experimental data really supports this finding. Okay, and now I'm going to just take 5 minutes to talk about the cytochrome C story. This is something where we're still trying to kind of think about what it all means and how it all makes sense. But cytochrome C, of course, is an electron transfer protein. And here's a picture of cytochrome C with one of his redox partners, cytochrome C peroxidase. And if you look at the cytochrome C, you have the heme here, axial ligand. Then you have the famous cis-XX-cis-his loop around here. That's the place where the heme is covalently linked to the protein. Right? Very important. Very important for cytochrome C. And the loop region here, you can see this is kind of right on the surface of the protein, right in the area where the redox partner binds. So if we look at just at the cytochrome C in this more space-filling model, this is what I had on my first slide. You can see here's the heme, right, and here's the cis-XX-cis-his loop, kind of looping around right on the surface of the protein. So we looked at this with nerves, with Cara Brandt from the University of Rochester, just having some fun with nerves. We measured here our spectrum, wild type, right, with wild type, everything just normal. You get that spectrum in black, and then when you do some C13 labeling of the heme, you get some spectral changes. But then what she did is they isobly labeled the peptide. Right? And remember, this is a nerve spectrum. All you see is iron moving around in its macrocycle, in its heme. But when you isobly label the peptide, you can see the heme vibrations are changing. And that's something I think that is underappreciated in the literature. It is something that, of course, is probably more pronounced for cytochrome C because you have this covalent link. Right? If you have your heme only bound like in myoglobin by electrostatic attraction, this effect is probably much smaller. But here in cytochrome C, where you have this covalent linkage, you can see that the heme is vibrationally strongly coupled into the polypeptide. And you can change heme vibrations by labeling polypeptides around the heme. Right? And so here's the picture I showed before. So again, similar thing. You have an experimental spectrum. DFT is okay, but not great. And you can refine this with the normal coordinate analysis. We already talked about this. So here's already the last slide then on this. So we see also, so we have the coupling between the heme, the dynamic coupling between the heme and the cis-XX-cis loop, which is right on the surface. That's the area where the redox partner binds. And so the question now is, does it have functional significance? And that's the part kind of we're still thinking about and designing new experiments to maybe come up with some ideas of what this could mean. Because you can think about when the redox partner binds to the cytochrome C, that this is a way to modulate now the vibrations of the heme, right? By making changes to the loop region, which is strongly coupled into the heme, you could minimize the organization energies for electron transfer. There's a way you could condition the heme for electron transfer. If you look at the ferric form of the heme, right, you have this one hole that you want to fill with an electron. You can direct that hole towards the periphery, this edge of the heme. That's kind of pointing out here by changing the normal modes of the heme, changing the dynamics. And so this is an interesting question now, is what the functional significance of this could be. And so we're still working on this. But again, this is something that originated by looking at nerves data, something that you would not be able to do in that way with resonance Raman spectroscopy. Okay, so I think time-wise we're pretty good. And that kind of gets me then to my acknowledgement slide. Of course, I thank you guys all for your attention. Here's a recent picture of my group, and I highlighted 3 people here who spent a lot of time doing nerves, especially Ashley McQuarters. She's right here. So on this picture, she probably thinks I'm done with nerves. And then Matt and Andrew are also here. They helped me with teaching the MCD module. So for Andrew, it's the first time here at Penn State. So he thinks this is really cool and exciting here. And I think Matt just likes MCD spectroscopy more at the end of the day. And with this, I would like to thank you all for your attention.
Does anyone have a quick question? Jeff, one quick question.
Do you have nerves of steel?
I think that in geology, people use this technique a lot. So if you ask who are the main users, people have studied lots of rocks, iron-containing rocks of this. So I could imagine that people look maybe at steel or other iron alloys to make some correlations there, maybe to like materials properties, right? So I don't know too much about it, but I could imagine that this is a way to look at this too.
I know that lots of people have to prepare. Will this, for the practicals, is there enough time if we start at 2, or should we start at like 10 past 2, 15 past 2? Is there enough time? I think stop, flow, freeze, quench, resonance, Raman, some others need to prepare. Would this time be good enough, or should we postpone by 15 minutes? Good enough, Bennett, or postpone? What was that?
Oh, thank you so much. That was really useful.
What did you say? Good for 2 o'clock or 2:15? What did you mean? 2.
I have a question. What are the